and welcome to Chapter 10. In Chapter 10, we're going to cover TCP/IP fundamentals. This is a really important chapter. There is a huge amount of information in here, and depending on your previous knowledge as far as TCP/IP, it may be pretty confusing. The video is going to be long, and there is a lot of acronyms and words. If you need to cut up the video and watch 20 minutes at a time, feel free, but there's a lot in here. So let's get started. We've finished our media and operating systems chapters, and now we're starting to work in addressing and transmission. How is data actually getting across the internet? How are we keeping track of the different protocols that are involved? I've included 3 different chapters in the addressing transmission section. So we're going to start that today with our TCP/IP. We're then going to move into subnetting with Chapter 11 and additional transmission information with Chapter 12. Okay, so best way to start with TCP/IP is to start with IP, Internet Protocol, and IP4, which is the one that most of us are most comfortable with. Most of the time, if you type in ipconfig or something like that into your command prompt, you will see a 4-octet IP address. Octets are 8 bits or 1 byte, hence the word octet, oct being 8 bits. So an octet. 8 bits in binary goes up to 256. So 255 technically. So if you have all ones, it's 255. All zeros would be 0. So when we're counting at 256 based, you can go up to 255 and then it rolls over and you start back from 0. You cannot have a 256 with an 8-bit number. So starting with that. So the examples that we've shown you here at the bottom are your IP address both in binary form and in decimal form. It's kind of hard for some people who aren't comfortable with base 2 to be able to see the difference between a binary and a decimal. Obviously, binary is base 2, decimal is in base 10. So as you can see in the binary form, you're looking at 8 numbers, zeros or ones, that form up to the number 256 in decimal. Most people don't read in binary, so we turn everything into decimal so that you can read it easier. And you can see kind of the binary range down at the bottom. We start from all zeros and then we slowly work our way up to all ones, which is 0 to 255. Okay, so recognizing that an octet, 8 bits, is 0 to 255. In an IPv4, so version 4 of IP, we're going to have 4 octets. So we're going to have 4 numbers between 0 and 255. And they're going to be broken up by decimals. So we put the first octet decimal, second octet decimal, so on and so forth. Every device that is on a network can be identified by its IP address. So we start, if we have multiple computers on the network, each of them has their own IP address. If you have multiple devices, they each get their own IP address. We've covered this in previous chapters. Each IP address is actually broken down further into 2 different values. The first part is what we call the network, and the second part is what we call the node. So the network and the node. The network tells you which network you're on, and the node tells you which device. We're going to get further into this with subnetting to break down how to do that, but let's just start at the beginning. So the network part is going to tell you which network, and the node is going to tell you which device. This is kind of similar to area codes. Now, in Montana, we're all 406, but in some states, they have multiple area codes. So the area code would tell you which network, and then your 7-digit phone number would tell you which phone you're actually on in that network, in that section. Same kind of concept. So when you think of your IP address, part of it is your network, part of it is your node. When we talk about which network you're on, networks are given a specific classification based on the number of nodes they need to be able to create. We have 3 different classes. There is also classless, which we will talk about in the next chapter. So let's think of these as classes. So first off, we have 3 different types of classes, class A, B, and C. Class A has the largest possible number of nodes, and class A always starts in that first octet between 0 and 127. 127, half of 256, so 0 to 127. It can have between 1 and 127 networks. There are possibly 127 Class A networks. Each one of those networks can hold 16,000 nodes because the other three parts of the IP address, the other three octets, are going to hold which device. First octet is going to tell you which class, which network specifically, and the next three octets are going to define the node. With a class B, we use those between 128 and 191. So half of the remaining range between 1 and 256. Those are going to be your class B. Class B is kind of mid-sized because we actually use both the first and the second octet to define class B networks. So class A networks, all we looked at was the first octet. Class B, we look at the first and the second to figure out the network. In this case, we can have 16,000 different networks because now we have 2 octets that we're working with for our network naming and 2 octets to define how many nodes. So 65,000 possible nodes and 16,000 for a class B. Then we get into a class C. There are, in a class C, we use the first 3 octets to define our network. So instead of just being the first octet or the second octet, we use all 3, and they start at 192 and work their way up to 223. We don't go all the way up to 255, but we'll talk about those in a minute. Those are reserved. So for a class C network, if your first octet is between 192 and 223, we are in a class C network. There can be 2 million possible networks in a class C network. These can be public IP addresses that are available as a class C network because there's only 254 possible hosts or nodes that are available for those networks because we're only using the last octet, those 255. And again, we don't use the 0, and we'll talk about that in a minute. So 254 possible hosts in a class C network. Really important to understand your different networks. You can identify your network by looking at that first octet, 0 to 127, or 1 to 127, 128 to 191, 192 to 223. That's going to tell you which class you're in. We use our subnet mask to define which network we're in, and we're using what we call a bitwise AND. So we're going to AND or do a logical AND between our subnet mask and our IP address, which is going to mask the node and give us just the network information. With a class A, all we need is that first octet. So we're going to AND it with 255, so we will get just that first octet number. With a class B subnet mask, you're going to have the first 2 octets as 255, and you're going to AND that against the IP address, and you're just going to get the first 2 octets. The other 2 numbers will be 0. Class C, your last octet will be 0, and you will just get the class C network. Remember, when we look at an IP address, we're breaking it down into network versus node. Network in a class C is the first 3 octets, so that's the thing we need to look at. Trying to be able to look at an IP address and be able to tell immediately what class are you in and what's my subnet mask. 2 really important things that you need to understand. As I said, class C does not go all the way up to 255. It goes to 223. There's also a series of reserved private IP addresses that cannot be assigned to public IP addresses. These are ones that are usually on your internal network, and you will find them in a network. When you log in, odds are your IP address is probably a 192.168 number. It might be a 172.16 number, and it might be a 10.00 number. These are possible reserved private IP addresses. The default for most Class C home networks is going to be your 192.168. Usually 0 or 1, and then 1 is going to be your router. This is pretty common, and this is a default. Because these are reserved, if you ever type in 192.168 and anything in the other 2 values between 0 and 255, you will probably not get a outside network. You will get something internal, or you'll get nothing. Because they're reserved. We can't make them public. They will never be a public IP address. So they're used internally. Obviously, we have more than the count that I gave you of networks going on in the world. That's because most networks have their internal network on one of these reserved IP addresses, and then they connect to the outside world with their public address. So they only need the one public address to get outside into the internet. But internally, in their inside company, inside their network, they're going to use these reserved IP addresses. The ICS is the Internet Connection Sharing acronym, and it's designed to allow a host to use network address translation, or NAT, to convert from a private to a public. Okay, let me explain that a little bit more, because NAT's really an important concept. Network address translation allows my computer at 192.168.116, whatever my computer happens to be, to use that private address, my 192 address, and talk to the rest of the world with my network's public IP. So my static IP from my house could be like 251, or I don't know, it's not that high. Sorry. 156, 227, 332, and 51. So that could be my outside public IP address. People can connect to me. I can connect to the outside with that IP address. If you go to the internet right now and you say, what's my IP address? You're not going to get your 192.168. That's your internal IP address. Network address translation is going to allow you to convert from your local internal private IP address to that public IP address that the outside world can see. So it kind of hides the IP address behind its service, the Internet Connection Service, that uses NAT, Network Address Translation. That way, if we're over at the school has an outside public IP address, but each of the internal computers has their own private address, which is part of that reserved group. They can keep using those internally, and then when they need to get outside to the internet, they can translate from their private out to that public outside one. There is a similar concept called port address translation, which is similar to NAT, network address translation, except it goes with port addresses instead of IP addresses. So you can do specific ports. If you wanted to run a Discord server, or you wanted to run a World of Warcraft server, and you want to open up a port and make that translation from your private IP address to the outside public, you can do that with port address translation to be able to open up a port. The ICS model is modeled here in that concept of your internal clients at 192.168.0. The gateway is going to be at 0.1, and then the internal clients are at 2 and 3. They can translate to the ISP IP address, which they have denoted here with X's, going outside to the rest of the world. There's a little image here of your basic IP config. You are going to get very comfortable with IP config by the time you're done with this course. Definitely by the time you're done with this chapter. IP config is the configuration settings for your IP address. Depending on your computer, depending on your server, depending on if you're on Windows, Mac, or Linux, IP config is going to give you your IP address. It'll give it to you both in IPv4 and IPv6 if you have it available. It will tell you what your gateway is, how did you get out to the outside world, and your subnet mask. Remember that subnet mask to be able to figure out what your network is. It also might give a little bit of other pieces of information that we'll get into as we go along. But being able to recognize your IP config. IP config has a lot of different controls that you can run against it. So you go to a command prompt, CMD, type in IP config. It'll give you some details. You can put ipconfig/all, and it will give you all of your details. You can renew and release your IP address, which we'll talk about when we get to DHCP. So we're going to do a little bit of history for a second on the DNS system. DNS is the domain name system. Obviously, every site, every public site out there has an IP address assigned to it. However, nobody's going to remember the IP address for Google or Amazon or Microsoft. So we don't use those. We use the DNS system to be able to associate an IP address with a given domain name. So we have our domain name, Microsoft.com, and it has an association between Microsoft.com and its actual IP address. DNS, the domain name system, takes care of that. The default DNS for Google is 8888, so 8.8.8.8. So you can use that as your DNS if necessary, but usually your router will have its own DNS and you can use that. The IP address is technically always faster because it doesn't need to do a DNS lookup. So if you've memorized your IP address, you are welcome to type it in and you'll get to the site just fine. Nobody does that. Everybody remembers the URL, the actual domain name, rather than the IP address. So that's where your DNS server comes in. If for whatever reason your DNS server does not have the ability to resolve the difference between an IP address and a DNS, having that IP address memorized is kind of useful because then you don't have to go through the DNS to do it. Understanding how IP addresses were created. So back in the olden days, there were not that many. They realized over time, the ubiquitous they, understood over time that we needed to kind of control what DNSs were being used, how they were being handled, what we were doing in that situation. So we started with the Integrated Network Information Center, or INTERNIC. INTERNIC was a government agency. It originally was owned by the government. And they organized what we call the top level domains, or TLD. You know how we love our acronyms. Our TLD, top level domains, may seem a little counterintuitive, but they're your .com, .org, .net, .edu, .gov. The last part of your domain name. We call them the top level domain because we actually look at the entire domain name slightly upside down. We look at it from the top to the bottom, with the top level domain being all the .coms, and then underneath that, all of the different addresses at different levels. INTERNIC wasn't able to really handle it. There was a lot of information that they needed to keep track of, and they ended up funding through the National Science Foundation the Internet Assigned Numbers Authority, or IANA, in the 1990s. These companies are still out there. You can still go to their websites and look them up. They're just usually consulted through to keep the sites updated. So the IANA in the 90s was still a government agency in the sense that it was funded by the government, by the National Science Foundation. And over time, they realized we really don't want this to be a government thing. We want this to kind of be a private industry so that it can handle anybody, regardless of what company, what country you're in, and so on and so forth. So they created the nonprofit private agency called the Internet Corporation for Assigned Names and Numbers, or ICANN. This imagery right here with the little global picture. It's a nonprofit. It is not designed to make profit, but it is also non-governmental, which means it's a private industry. They handle the registrar to keep track of your IP addresses and domain names. They consult, or essentially allow, outside registrars to sign up to be a registrar. Yes, I am actually putting an extra R in there. It's not register, it's registrar, R-A-R. Make sure you can spell it correctly. It's kind of a hard one. A registrar, who is the guy who registers you. The registrar is a outside entity that has associated with ICANN to be able to say, yes, I am an official registrar. People are going to come to me. I am going to fill out the paperwork and get everything registered with ICANN so the domain names and the IP addresses are together. We're going to talk about different things you can add to your registration to make sure that you can find your domain name with specific IP addresses and so on and so forth. But understanding that a registrar, R-A-R, registrar is the guy who allows you to register your domain name with a specific IP address. So if you have a website and you're hosting it on Azure, and Azure has a specific static IP address that they have given you for your website, you can go to the registrar and you can say, I want mycompany.com to be at this address. And they will make that link and update it to the entire DNS system. So when someone types in mycompany.com, they go straight to your IP address and they make that connection. So it's important to keep track of that. There's lots of them. There's some that are better than others. There's registrar.com. There's GoDaddy. They have their own registrar inside of it. And there's a lot of others out there. You can obviously do an internet search to find them. But they will go through and do that registration for you. At this point, we're going to stop a little bit and start looking at what is a domain name. So I just talked to you about how we're registering the domain name. Now let's talk about what that means. What is a domain name? First off, a fully qualified domain name, FQDN, must contain both the domain name and the host. And we're going to talk about the different obvious hosts as we go along. So what device or what actual computer are we going to? It needs to have the host, it needs to have the domain name, it needs to have the top level domain. Fully qualified domain names are limited to 63 characters. So when you are coming up with your company name, try to avoid a 23-letter company name just because there's a limitation. 23 should be fine, but try to avoid something really, really long because there's a limitation as to how large your fully qualified domain name can be. It can only be 63 characters. And it cannot use any special characters, no slashes, no stars, things like that. You don't want to put those in there. When we look at our domain name, as I said, we look at it from the top to the bottom. Top level domain is your .com, your .org, your .edu. This is your TLD, top level domain. Underneath your top level domain is your second level domain. Your second level domain is what most of you probably think of as the domain name, gfcmsu.edu. That's actually a second level domain because our top level is just the edu. So our second level domain is all of the schools that are under .edu, and they all have a second level domain. Underneath your second level domain is a subdomain, which is any level beneath your second level domain. So if we broke up the school into administration, HR, students, we could have students.greatfallscollegemsu.edu, and that students would be a subdomain. Subdomain, second level domain, top level domain. Understanding that your domain name, your fully qualified domain name, has to include all three. Just having a second level domain and a top level domain will work in a lot of cases, but you might need to add that www to the front to be able to get to the website, or an FTP to the front to be able to get to your FTP server. You need to understand how those work. You can set up every time you go to mycompany.com, go to this specific location, and that works as well. But you have to have that set up directly. Otherwise, you need to include a fully qualified domain name. A resolver is a software program that exists on your host that asks the DNS server to convert the host name into an IP address. So if I want to get to mycomputer.com or my computer on my network, I know my host name, my computer, but I don't know my IP address. So the resolver is going to go to each of the different servers as necessary until it can resolve that IP address. If you have multiple servers at multiple levels, say one of the larger companies that has top level domain server, secondary level domain server, subdomain server, each of these, depending on how you need to resolve it, you may only have to go to one. If I'm staying inside my network, I may be able to be just fine staying just at my subdomain server and then go back to my computer. I might have to go up to the secondary level, and I may have to go up to the top level. I may have to go all the way to the root and then come back down. So depending on how you're going to navigate the tree of different DNSs is going to be how far you have to go. But the resolver, the important thing is to remember what a resolver does, resolves that host name, so whatever the name is that you're going to use for your host, into an actual IP address. This is being done through your DNS, through your DNS server, to figure out which IP address goes with which actual computer, what actual IP address. When you set up your DNS records, and this is important, there's sections of Packet Tracer that you can go into to set up how to do your DNS records for specific servers. When you're going to make that connection, this IP address goes to this computer. There are a couple different types of records you can store. These are important because each of them does something a little bit different. The first is your A record. Sometimes they put it as 4 A's, AAA, or it's your A record. This is the forward record that says it's a link from this domain, mycompany.com, to this IP address. You have to have this. This is the important part of recording things with a registrar, is to be able to say mycompany.com goes to this IP address. There is also what we call a PTR record, which goes the other direction. It links the IP address with the domain. So if someone types in the IP address, that also goes to the domain. We call these reverse records. Forward records, reverse records. So PTR and A records are opposites of each other. But they keep track of, if someone knows the IP address, what's the domain that it's associated with. Important to keep that. You can actually go check those out online to find out what IP address does it associate directly to a domain. How do I find that? Your SRV is your service records, and these define different services that your IP address may do. So depending on what services your server is running, and it can run multiple different types of services, those services are identified by an SRV. So if you're going to have a webhook to allow website services or web servers, things like that, you can set those up as different SRV records. The MX records identifies email servers, specifically email, because email servers really don't care about anything else except other email servers. So identifying your IP address as an email server is important. So your MX record stands for your email. That handles that. A lot of people put a CNAME record in, and it's an easy name for individual resources. So again, if I want to have a CNAME to define my web server as opposed to my database server, as opposed to my file server, I can set up different CNAME records in my DNS record list to be able to make it an easy name to be able to get to that. If I wanted ftp.greatfallscollege.msu to go somewhere, I can put CNAMEs in there, and it'll provide an easy name to be able to associate a name with an IP address. And finally, there is the SPF record, which is the Sender Policy Framework, SPF. These are email servers that are authorized to use a specific domain. So again, MX records identify them as email servers. SPF authorizes them to actually use the domain. These different record types are important. It's really important for you to understand the difference between an A record, which is useful, a CNAME, and the MX records. Those are the ones that are associated with your email, being able to have an easy name for your resources, and then of course your obvious direct link. You have to have an A record. In your computer, you probably have a file called hosts. It may be a text file or LM hosts. These are going to be a relationship between your IP address and the actual FQN, so fully qualified name, or computer name in Microsoft. These are text files. They can be modified with Notepad. They're just plain ASCII files. And the computer is going to store those. The nice thing about this is the more sites you go to, the more your host file gets filled in. You don't have to go to a DNS to go find it. You can just look at your host file to associate. I'm going to go to Amazon.com, and it's going to link me directly to the IP address. So this is going to help your computer to handle this. Originally, the Windows Internet Naming Service, WinS, resolved the NetBIOS name and the IP address, similar to an LMS or LM hosts file. Same kind of thing. So you're going to want to remember that WinS, the Windows Internet Naming Service, is the service that resolved your NetBIOS name, specifically on a Windows machine, with your IP address. Okay, now that we've kind of beat up IP addresses for a little bit, got our DNS out of the way, got that understood, let's start talking about TCP, UDP, and IP. The suite of protocols. It is not one singular protocol. Thinking of TCP IP as a singular protocol is going to confuse you. It's not. It's a series of protocols. It's a suite of protocols. Like Microsoft Office is not a singular thing. It's Word and Excel and PowerPoint. TCP IP is not a singular thing. It is TCP, IP, UDP, FTP, DNS, DHCP, so on and so forth. So TCP IP is the basic suite of protocols that we use by default across the internet. If you are doing anything with networking, understanding TCP IP is really important. We bring up our OSI layer here to look at the different things that each of these protocols does. Starting with IP at the bottom. So we've got our Ethernet and our token ring and our FTDI hanging out at the bottom. They're hanging with our physical and our data link, layers 1 and 2. They're dealing with frames and they're handling those. Okay, cool. Now we're going to get to layer 3, the network layer. Network layer is IP. IP, Internet Protocol, is designed for the logical addressing of both connection or connectionless. Doesn't matter if you have TCP or UDP, you're using IP at the bottom. So IP is going to be your layer 3. IP handles the packets. It addresses them. It handles the IP addresses, hence IP address, because it handles the addressing. It works with both connection and connectionless, and it is that third layer on the network layer of dealing with your packets. Up one layer, our fourth layer, are TCP and UDP. Remember, TCP, Transmission Control Protocol, and UDP, User Datagram Protocol. Both of them handle the idea of sending information. TCP is connection-based, so it regulates the connection, and it handles that flow control to make sure that things stay together and that connection stays stable. UDP is connectionless, so it's just sending packets. Sending a packet, sending another packet, sending another packet. So it's sending packets down to the network layer, and then it's receiving the packets and segmenting them up into raw data that it can pass up in the protocols to 5 through 7. So both TCP and UDP exist at that fourth level, the transport level, and they handle it both directions. It's important to recognize, and we've done this before, we've talked about this, the idea that data comes down from the application onto the media, and then comes up from the frames from the media and goes up through packet segments and then back to the raw data to get to the other side. Data is moving down onto the media, back up. So as long as we can follow that kind of logic of where the data is going, you can try to understand how IP is going to handle the addressing to go down into the packets and the frames so it goes further down, and then receives the frames, breaks up the packets into segments, and moves it the rest of the way up. TCP and UDP, take your raw data, turn it into segments, break it into segments, send it down into packets for the IP, and then take those segments, the packets from IP, up, turn them back into segments, and push them up as to raw data, back up to that 5 through 7. Couple of extra protocols that exist in this group. Obviously, we brought up FTP, File Transfer Protocol. DNS we've covered, so the Domain Name Service. DHCP, we will get more into the ability to dynamically assign your IP addresses. So DHCP is a dynamic host configuration protocol. DHCP is the thing that assigns you an IP address when you connect to the network. So you're walking around with your computer and you walk into a location with a network and you plug into the network, either hardlined or wireless. When you plug into the network, your DHCP is going to assign you an IP address. Can't do anything until you have an IP address. Once you get an IP address, now you can talk to the network and or talk to the internet through the network's line. LDAP, Lightweight Directory Access Protocol, keeps track of the different nodes that are on your network. So I have my network and I've got 43 computers on my network. LDAP is the directory access. It's the phone book, the thing that controls what is it that you want to find. I want to go find John's computer. Okay, let me go look in the phone book. Let me go look at LDAP. And LDAP is going to tell me, oh, John's computer is at 192.168.17, whatever it is. Wherever John's computer is. So your LDAP is your lightweight directory access protocol. There are multiple versions of LDAP, as we've covered in previous lectures, that are proprietary based on the company who built them. But LDAP is where it all started. This is your basic address protocol. SIP is your session initiation protocol. And SIP, or SIP, is designed for your voice over IP or your video, your Skype calls, your Teams calls. Session initiation protocol, it's really important in these calls, any of these types of calls, these connections, that they stay connection-based. So your SIP is going to be the initiation protocol that's going to start the session and keep it running. It establishes that session for your voice over IP or your video, because we need those to be going continuously. It's like a regular phone call over the phone. If it wasn't connection-based, you would get spaces and it would sound weird. So we need SIP to be able to keep that straight. Understanding the different frames of UDP, TCP, and IP might help you to kind of visualize that difference. We've talked about how IP encapsulates TCP and UDP, and Ethernet encapsulates IP, and TCP encapsulates ARP, or whatever frame it is that we're up above that. Looking at the different frames, you may be able to see some differences. So if we start with the TCP versus the UDP, remember, TCP is connection-based. It needs to keep track of things like acknowledgements and flags and sequence numbers, pointers, options, all of these kind of things. They go into a TCP header. UDP doesn't need all of that. It needs the source, the destination, and the data. Throws in a message length just to make sure you know how big it's going to be, uses a checksum for error checking, but essentially it's much simpler. You can see UDP frames really have mostly data, whereas TCP frames have a lot of extra header information to make sure we keep things straight. It's important for frames to keep all of their data. The IP frame has additional information as well, and then it will include the data from its previous frame. So you can see that the IP frame here takes the header information in the IP in addition to the TCP frame or the UDP frame. It encapsulates it. So when you look at an IP frame, inside of the IP frame is some information from the TCP frame or the UDP frame. An important thing to see here, TCP and UDP refer to the source port. IP refers to the source address. Remember that port, and we're going to talk about ports in a second, that port is going to be specifically a specific port on your frame or on your computer that you're going to be referencing. We'll talk about different ports. The IP doesn't worry about the port. That's included in the TCP or the UDP frame. It cares about the IP address. So the IP address is the thing that the IP frame is storing. The port information, source and destination, are in your UDP and TCP. We also include a couple of other things like which protocol, time to live, different flags, how long is it, things like that are all going to be included in the IP header. The IP header is going to include all of these extra IP things. The datagram data inside of the IP frame, that's your whole TCP or UDP frame. IP encapsulates your UDP and TCP. So when we look at our Ethernet frame, it encapsulates our IP frame. The Ethernet frame is going to include the MAC addresses, because now we've converted that IP address into a MAC address by the time we got into the Ethernet frame, and some error checking there as well. We like to do error checking. So you can see from TCP and UDP into the IP frame into the Ethernet frame. And you can see on both the TCP and UDP frames, the IP header section that sits there in the Ethernet frame, that's going to be your IP frame information, encapsulating that. At this point, we're going to talk about how IP is going to address your IP addresses. We have to assign them. How are we getting them? How are we getting our IP addresses? And this is where DHCP really comes in. There are two different ways that you can assign your IP addresses. You can statically or dynamically address them. Static versus dynamic. Static, meaning they stay the same and they don't change. Dynamic, meaning that they do change and they are constantly being updated by the server who's keeping track of them and making sure that everything stays fine. Static or dynamic. If you are statically addressing your IP address, you are assigning a specific IP address and it doesn't change. So you can say, I always want my printer to be at 192.168.115. That's my printer. And I want it static and I don't want it changing. You can do that with a static IP address. Originally, this was done by WinS. So Windows Internet Naming System would deal with the assignments. We all now use DHCP. DHCP, again, Dynamic Host Configuration Protocol. The server on your router runs your DHCP, and it dynamically assigns an IP address when the computer logs onto the network. So you log onto the network. You don't have a static IP address. You have a DHCP address. So we're going to go over this to the router, and we're going to say, hey, hi, I'm new here. Can I have an IP address? And he's like, totally. Let me go look at my address pool. You can pool or create a collection of IP addresses that can be dynamically assigned. Usually you give a start and an end range. So I want to start at 192.168.110 and I'll go up to 100. Or I'll start at 100 and I'll go up to 200. And these are the possible IP addresses that you can have in my pool. So when I come over and I say I'd like an IP address, he looks at the pool and goes, are there any addresses available? Yeah, let's give you the next one in the list. Here you go. And he gives you what we call a DHCP lease. We are using that IP address for a given amount of time. As you use the computer on the network, you can keep talking to the router and say, hey, just letting you know I'm still using that address. And he's like, cool, I'll go ahead and renew your lease for another day, for another 5 hours, for another whatever you have for your timing on your lease. In your pool, you can also specifically exclude IP addresses. So if I did want to have a static IP address for my printer at 15, I can exclude that from my pool to make sure no one ever gets that IP address. We don't want to have duplicate IP addresses. So obviously, if I'm going to statically assign addresses, I can statically assign you to 15, but I'm not going to statically assign my printer also to 15. If you have competing duplicate IP addresses, everybody stops working. Nobody works when you have competing IP addresses. So it's important that if you are going to statically assign an IP address, that you're going to be fine. Sometimes you can't get to the DHCP server. I log into the network, and for whatever reason, the DHCP server is down. There's collisions on the network. For whatever reason, I cannot get to the DHCP server. I may not actually have a cable attached. The cable may be the wrong kind of cable. I may not have access, whatever it is. I can't get to the DHCP server, so I can't get a dynamically assigned IP address. If this happens, your computer will assign you an automatic private IP addressing. Yes, it is a letter or an acronym that goes back and forth. APIPA. APIPA. So your automatic private IP addressing. Automatic private IP addressing. Your APIPA. And it is always 169.254. And then some series of numbers. If you ever see 169.254, there is a problem with your DHCP server. Either you can't reach it or there's a problem with the server itself. But that number is consistent across all networks. If you ever see 169.254, you cannot reach your DHCP server. You cannot get a dynamic address. You can choose in your network setup to always use automatic private IP addressing and always use 169.254. What this will do is it'll mean you'll never use the DHCP server to be able to do addressing. You'll have to figure out some other way to get information, or you really don't want to be on the network. You don't want to be available for the network for any type of communication. Generally, though, it's going to be a sign that your DHCP server is a problem or you can't reach it. So you can see in the little image down here, each of the different stations has gone through its hub, and then it's gone over to the server where it has asked for a DHCP dynamic address. We can add in 2, 3, 4, 5, 6. And if one of those comes off of the network and plugs back in, he may get a different network or IP address next time. It's really important to understand if you are using dynamic addressing, you may end up with a different IP address next time. If you are doing anything that required you to put in an IP address or store an IP address to break through a firewall, here's my IP address, those are going to change. So dynamic means that it will constantly be changing. I mentioned that we were going to talk about ports. The port number can be used to create an actual virtual connection between two computers, just like taking two computers and plugging them in together. When we take our IP address and we attach a port number, we now call it a socket. So it goes from being just a regular IP address and a regular port number to being a socket when you combine the IP address and the port. Couple of things about ports. Ports are technically 16-bit numbers, which means they can technically go up to the 65,000s, which is fine. Ports numbers 0 through 1023 are actually assigned by IANA. So IANA has defined ports 0 through 1023. Those are already kind of set aside and used. Ports 1024 to 49,000 are designed to be assigned by individual pieces of software. That software can include your LDAP or your voice over IP or your tunneling or your SIP or your PC Anywhere or your Skype or your FaceTime, whatever it is. So those ports are all software specific up to 49,000. Anything over 49,000 is just wide open. They're available. So you'll find things like Discord servers, things like World of Warcraft servers are going to be in those 60,000s because they can. Those are just available and open to anybody. Again, 16-bit numbers, if you're looking at bits, 16 bits goes up to the 65,000 as possible decimal versions of those numbers. A couple of ports to remember, and this chart is really useful in a lot of different ways to keep track of which port refers to which protocol, which port refers to which server. Really important ones for the Network Plus test, 20 and 21 are both FTP. One handles the data, one handles the commands. So the control commands are 21, the data is at 20. So if you're going to use FTP, you're using 20 and 21. Telnet uses 23. Secure Shell is kind of useful at 22. HTTP and HTTPS are 80 and 443. You might see that 80 a lot if you're using HTTP, and then if you're using secure HTTP, HTTPS, you're using 443. These different ports are the ones defined for HTTP. 110, 143, and 25 are POP, so POP servers, post office protocols for mail. IMAP, which is related to mail as well, so the internet messaging protocol that we use for that. And SMTP, which is your simple mail transfer protocol. These are, again, mail protocols. So these deal with your email. So those are really important ones to remember. Like if you were writing notes to say which ports do I need to memorize and you were pasting them on your computer right now, these would be the ports I would write down. There are obviously other ones, and yes, you still have to know them. You have to know that the 17, 19, and 20 are going to be your video and voice connections with your H323. You kind of have to know that your DNS is at 53 and your DHCP is at 67, but those aren't as significantly important as your FTP, your Telnet, your HTTP, HTTPS, and then your mail protocols. These are the different ports that you're going to use. Remember, a port plus an IP address, so you would say 192.168.1.1:80 is going to be my mail or my web server sitting on my site. So your port and your IP address together make a socket. Okay, at this point we're going to introduce IPv6. So we've been doing everything in IPv4, mostly because it's easier to say the number. But IPv6 is technically classless. Okay, so what happened? We had IPv4, and IPv4 was fine because there were 17 computers in the whole world and everything was fine and there was no problem. Obviously, the internet blew up and everything was great and everybody had IP addresses and everybody was asking for things. The 4 octets that we get with IP4 is not enough to cover every computer in the world. Obviously, that's insane. We didn't really expect computers to get that big, we being the universe that made internet. So we created IPv6. It actually started in the 90s and it's worked its way up to being the new way of doing things. IPv6 is harder to say and it's harder to define, or it's harder to write out, but it also has plenty of options. IPv6 is 128 bits, which are separated into 8 16-bit blocks, separated by a colon. Each of those 16-bit blocks is identified by a 4 hexadecimal number, by 4 hexadecimal numbers. So hexadecimal, 0 to F, are 16-bit numbers. So each of those 16 bits can be recognized, and you end up with a 128-bit number. Being able to look at an IP address and go, that's an IP address. Being able to look at an IP address and go, wait, it only had 7 instead of 8 16-bit blocks. There's something wrong with it. Being able to look at an IP address and go, that's the one I want, or that's not going to work. When we introduced IPv6, there are now 2 to the 128th or 3.4 times 10 to the 38 possible addresses, which means every single person could have thousands of addresses assigned to them, and we still haven't run out of IP addresses. There's a lot of choices here. It reduces broadcast traffic because it uses what we call neighbor discovery instead of ARP tables. Neighbor discovery is in the data link layer, and it's used to identify different network addresses. Because every computer gets their own network address, we don't have to go through address resolution to check things. When you do address resolution, you ping them, they respond, you ping back, they respond, then we kind of make sure we know each other. Neighbor discovery avoids all of that conversation. So it reduces traffic on the network, which makes your network cleaner and there's less traffic across it. The more computers you have using IPv4, the more your ARP tables are being used, the more communication, the more traffic on your network. It also uses IPsec, or improved security, or IP security, to encrypt and authenticate. So the IPsec is the encryption and authentication that we use on IPv6. It's important to recognize that also made IPv6 safer. Okay, when we look at an IPv6 number, remember, they're all hexadecimal numbers, so any specific individual number can be a number or a letter from 0 to F, 9, A, B, C, D, E, F, to make 16 bits. There are technically 8 groups of numbers. Each is separated by a colon. However, in a lot of cases, if you have a 0, you don't want to have to write out 0000 because it takes up a huge amount of space and it's irritating. We like to shorten things down. So if you have 4 zeros, you can shorten that to a singular 0. So 4 hex zeros can be just a single 0. If you have multiple groups of zeros, you can put 2 colons to identify multiple zeros. You can only do it once. You can only have one 2 colon instance in your IP address, your IPv6 address, but you can do that. So the example up at the top here with the FE80, I could put FE80 : 4DE1 FO1B, so on and so forth. And the : tells everybody everything that you expected to be in between these two is a 0. The reason you can only do it once is because if you had that twice in 2 different places, you wouldn't know how many zeros there were in each instance. In this case, because of the other count of colons, I know that there must be 3 groups in here of 0 because I only have enough numbers to fill out the other 5 specific entries. If you had 2 of those, you might have : in one place and another, and you weren't sure how many of those were 2 zeros and how many were 3, and so on and so forth. So you can do the zeros and you can do the : When we look at a MAC address specifically is the 6 hexadecimal, 2 hexadecimal numbers. So there's a total of 12 hexadecimal numbers. If you wanted to convert a MAC address into an EUI64 identifier, which is the IPv6 version of a MAC address. So MAC address, remember, MAC address assigns a specific number to the node, to the specific thing with the IP address or with the network card. The MAC address has 6 2 hexadecimal numbers. In an IUE64, so the IPv6 version, instead of being the first 3 are the manufacturer, the second 3 are the unique ID, the first 3 are still the manufacturer, and the last 40 bits or the last 6 numbers or 5 numbers are going to be your unique identifier. We actually add in FE and FF specifically into that 2 space to make it into 8 hexadecimal numbers. So you can convert your MAC address to your EUI24 by being able to add in FF-FE right in the middle, just to add those to the front, and then be able to expand that upon. As time goes on, that probably will not work because we're going to be getting rid of MAC addresses and moving towards EUI64 identifiers. So in the next 5 to 10 years, that may change. But for right now, if you have a MAC address that is a regular IPv4 version or 6 hexadecimal numbers, 12 hexadecimal numbers, 6 groups, this is how you convert them to a IPv6 version. IPv6 is technically classless. However, we do differentiate between specific addresses for individual network usage. 3 different types of IPv6 classifications. We have our global address, our link local, and our unique local. A global address is similar to an IPv4. It's a public address. You can forward to it. It's like a normal IPv4 address that goes out to the internet. So the global address is kind of that outside address, and it goes through a global unicast, and we'll talk about that unicast in a second. Link local individually segregates portions of your network, separated into groups. Again, HR, students, instructors type concept. There is no forwarding inside of a link local address. So we don't do forwarding inside of that. It's just separating individual groups to specific locations. Your unique local allows you to forward from inside of your network without going outside. So anywhere in your network, you can talk to those computers. Kind of like being able to have your internal network IP address that is not a global IP address. It's your internal network. Same kind of concept. So we can forward packets from anywhere inside of our network, but it is the entire organization. Whereas link local defines a specific location that is a separated group of computers in your network. Now, I threw out the word unicast, but I didn't explain when I did what it meant, because we are going to have the whole slide explaining IPv6 addressing. Okay, IPv6 addressing. We have the options of unicast, multicast, and anycast. Unicast is going to be your single network address. We are going to send it to a specific address. Unicast, one cast into a specific cast. Multicast delivers to multiple addresses, any address that exists in the grouping that we're using for our multicast. Anycast actually says, send me to the closest thing that has some piece of information that I can use, the nearest interface. So it doesn't say send it to a specific interface, a specific router, a specific computer. It is literally saying send it to anybody that will respond with an answer. We can do this in the situation where I'm just going to send you to a router and get the DNS tables back or something useful in that situation. So we can do an anycast. Of the different unicast options, we go back to that global, link local, unique. So your global, similar to an IPv4, always starts with a 2000. 2000 is always its prefix, and it's a global unicast saying I'm going out. Our link local unicast is used to communicate on the LAN or on the network, but it will not be forwarded by the router to the outside world. This is similar to the API-PA address, and it always starts with an FE80. So the API-PA, remember, does not go through your DHCP to assign a specific address. It is a local IP address that is only used within your network. You cannot do any forwarding. A unique local unicast is a replacement for the site local. So let me explain what site local is. Site local technically has the same function as an IPv4. So your private 192.168, again, not routable with it beyond the LAN, and it always starts with an FECO. Site local stopped getting used, and we've kind of replaced it with unique local. So they're similar. They do the same functionality. But the unique local starts with FC00 instead of FEC0. All of those prefixes are in your book, and they're also listed out here what the different prefixes mean. The prefix is a fixed value for that first section, that first little section of 4 numbers that is going to explain what you're going to do with that IP address. What is it going to be used for? Is it going to be a global unicast? Is it going to be a local unicast for your unique local, site local, or link local? Is it going to be a multicast? Is it going to use different pieces of information? All routers, all nodes, so on and so forth. We barely touched on the concept of a loopback address a couple of chapters ago, but let me rephrase those again. A loopback address is the reserved address that you test for functionality. If I type this in, I should get back an address that says everything's good, everything's working, or no, it's not. In an IPv4, it's 127.0.0.1. The IPv6 is all zeros with a 1 on the end. With the shortened notation, : 1 will tell you that it's all zeros. So that is your loopback address, reserve address just to test for functionality. Your unspecified address is used to check for duplicate addresses, and it's all zeros in an IPv4, and it's all zeros as well in IPv6, or simply 2 colons in the shortened version, because that will tell us that it's all zeros. So this is the unspecified address and the loopback address. Understanding that these addresses are reserved and they're only used for specific purposes. When we want to convert from IPv4 to IPv6, we use some transition technologies. There's 3 of them that we're going to talk about. They're in your book, and they explain the different ways that we can convert from a IPv4 to an IPv6 so that things can be run that way. We can also go the other direction. 6 to 4 is a way to communicate with IPv6 using the IPv4 internet protocols. It's designed to be used router to router. So specifically one router to the other and be able to talk together. It always starts with 2002, : that's its prefix. And then it uses 16 bits or 8 16-bit numbers. So in this situation, we are defining them as WW, XX, YY, and ZZ. What are the 4 octets for your specific IPv4, where WW is the first octet, XX is the second octet, YY, and ZZ. So when we take those 4 numbers from our IPv4 and convert them into an IPv6, we turn those into hexadecimal numbers. So 134 would be shortened down to 86. 86 is a hexadecimal version of 134 as a decimal. AF is 175. So on and so forth. 1B is 27 and 0A is 10. These specific numbers can be converted to turn your regular basic IPv4 into an IPv6. We add 2002, : and then put in 2 more sections of hexadecimal numbers to make a full IPv6 number. This is your 6 to 4. You can go the other direction as well. So if you have a 6 to 4, if you have 2002, 86AF, 1B, 0A, you can convert that down into 134, 175, 27, and 10. So if you ever see 2002, : know that the next couple numbers are going to be zeros, and then you're going to have those 2 sections, which you can convert down into your IPv4. ISATAP is the intra-site automatic tunneling address protocol. Microsoft and Cisco got together and they decided to make this protocol to be able to tunnel an IPv6 address inside of an IPv4 packet. This is designed for node to node or specifically node to routers. It does neighbor translation or neighbor discovery as well. So it allows you to use that information to be able to turn your IPv6 from a singular node to another node or to a router. So that's this one. If the ISATP is not available, we can use something called Tirado, which is similar to network translation and does a tunnel that is similar to 6 to 4. So these are the different IPv6 translation technologies that we use to convert from IPv4 to IPv6 and vice versa. Okay, couple extra things as far as IPv6 before we move on. I know we're almost done. I appreciate you being patient and getting through this. IPv4 or IPv6 information. First off, broadcast by definition sends it to all network addresses. Multicast sends it to a specific group of network addresses. In IPv4, we can do the multicast address of 224, 252, or specifically when we're doing multicast. With IPv6, multicast starts with FF02, and then we go to 13. That's the multicast address to send to specific addresses. IPv6 only actually uses multicast because it uses specific prefixes to do unicast or broadcast. So there is no broadcast in IPv6. We just use a multicast that tells us with that prefix what we're going to do. So if you struggled with the prefixes before, you might want to go back a couple slides to where we have the prefix list and show you those prefixes are used to define whether you want it to be broadcast or multicast or unicast and in what situation. IPv6 has lifetimes, just like regular DHCP is going to assign a lifetime. Generally, we have a valid and a preferred lifetime. A valid is usually a week and preferred is usually a day, but those can be modified by your server on how you want to do them. DHCP with IPv6 uses specific flags. They have an M flag and an O flag. And each of these flags are going to determine different pieces of information from your DHCP server. If the flag is 0, so these are Boolean flags, 0 or 1, 0 means no, 1 means yes. The M flag means that you will get an IP address. A 0 for the M flag would mean you don't need one. You're static. You don't need an IP address from the DHCP server. The O flag, no or yes, is going to tell you whether the computer will get the other data. Who's the gateway? Who's the DNS server? Other pieces of information. If the O flag is 0, you won't get that information. If it's a 1, you will. So DHCP is going to use that M and that O flag to determine what pieces of information you need. When we have IPv6 on Windows, originally, even way back with XP, it was installed or it was allowed, but you had to manually install it. So you would go to a command prompt and you would type install IPv6 or uninstall IPv6. Now it's supported by default. It's already done in your computer. If you have a Windows machine that's Windows 10, you're fine. It's already done. All right, we are almost done. Troubleshooting. These terms you need to memorize. You need to know what each of them does. You need to know what it looks like. You need to go over your computer and play with them right now and see if you can get them to work. Starting with netstat. Netstat with a -A is going to display your current TCP, IP, and port statistics. Tell me about your TCP and what ports they're using so that I can keep track of that. That's netstat. NBStat is your net BIOS. Net BIOS as opposed to network. Net BIOS statistics. And it's the net BIOS over TCP statistics. So those two are similar. They're both statistics. One is your whole network, your TCP, IP, and your ports. And the other is your net BIOS. NB for BIOS. Pinging. At some point, you probably pinged before. So pinging is simply sending a packet from one host to another, and then the packet echoes a reply. You can do ping-4 to enforce an IPv4 or ping-6 to enforce an IPv6. So if you want to use pinging with an IPv6, you can use ping-6. In a Windows machine, you have trace route with an RT, trace RT, or trace cert if you're looking at it and trying to figure out what it is. The other is trace route with the word spelled out. Trace route is a Unix command. Trace cert is or trace RT is a Windows command. They send a packet and then they gather information as they go. So as they're going along, they're saying, I went to this guy, then I bounced off this guy, then I bounced off this guy, and then we're good. So this is the different trace routes that you're going to be taking when you do a ping. It's a ping attached to all the statistics along the way. Your ARP tables we've talked about. So ARP is your mapping your map address to the IP address. Start with the IP address and end up with MAC address. Your reverse ARP, or RARP, is the other direction. Start with a MAC address and give me an IP address. If you give me the MAC address, I'm going to give you the IP address. So reverse ARP and ARP are exactly the same thing. They're just backwards. Your NS lookup. So I'm going to look up the network, and I'm going to query the domain servers to look up the domain names and IP addresses. So I'm going to give an NS lookup for a specific address. In the example here, I called Google. So I did an NS lookup for Google. From my computer, the server doesn't know who Google is. I am currently at 10.0.0.1. That's my router. But they do say that www.google.com is at this address, and you can see that they gave me both the IPv4 and the IPv6. The final is TCP dump, which is a Unix command similar to a packet sniffer. It reads all the packets by your network card and then tells you what they are. This is similar to what we're seeing in Wireshark. I'm really proud of you for making it to the end. I know this was a very long chapter. Again, huge amount of information, as you will see by the 23 sections in your study guide. If you want to do the review questions, great. Study guide 10.1 through 10.23, that's your assignment. The labs, there are 6 labs. For your labs, I actually recommend spending a little bit of time with Packet Tracer just because you need to start getting comfortable with a simulated environment. Obviously, if you're taking the Network Plus test, you need to be able to use a simulated environment and understanding how you can click on a router and be able to set up the DHCP server on a router, being able to connect multiple computers to it, so on and so forth. So I recommend spending a little bit of time there. If you have the ability to do this at home, great. But I would recommend using Packet Tracer for some of them, especially Lab 49. 50 and 51 use Wireshark. If you have any issues with completing your labs, go ahead and enter in the comments. I couldn't hook up to a second computer. I don't have one. I had trouble with this part of the lab, but still fill out the review questions. Those are required. And you shouldn't have to do any of the labs to do the review questions. The review questions are more of knowledge that you should have gained by doing the lab. If you weren't able to complete the lab for whatever reason, just include a note at the bottom that says I wasn't able to complete the lab because blank, blank, blank. That's the process of the lab. If you did the lab and you had troubles, or if you did the lab and you had comments, include those in the notes as well. Make sure you do the review questions. Obviously, the study mate's available, and don't forget to take your quiz. I hope you learned a lot about TCP in this lecture. I know it was incredibly long. Please let me know if you have any questions. You can always post in the comments or send me a chat. And I hope you have a great week. We'll come back next time for subnetting.